Black holes are massive, the densest objects in the universe. They have such a great mass that their gravitational pull doesn't let anything, even light, escape their clutches. But in this terrifying world of black holes, there are monsters that are in a league of their own. Recently, astronomers discovered a black hole that is 33 billion times as heavy as our Sun. This space giant sits at the center of a supergiant elliptical galaxy called Abell 1201, which is located 2.7 billion light-years away from our planet. This black hole is so large it was given a rare designation, an ultra-massive black hole. No wonder. It's more than 8,000 times heavier than the supermassive black hole at the center of our home Milky Way galaxy. This ultramassive black hole was the first one to be discovered with the help of gravitational lensing. This method is based on the fact that very massive objects such as galaxies bend the light from a more distant object, magnifying it. A great thing about this method of research is that it allows astronomers to study inactive black holes too. It could help us detect loads of new black holes beyond our universe. That's what the area surrounding our galaxy is called. Probably it would help us find some exotic objects we've never seen before. Now, let's speak about another awesome instrument that efficiently helps us explore space, the James Webb Space Telescope. When it stares at young galaxies, which would look like mere red specks to you, it sees an astonishing number of cyclones churning at their centers. Those are black holes. Interestingly, giant black holes were believed to be big players in early cosmic history. But James Webb regularly finds an unexpected number of these beasts. For example, using the telescope, astronomers have detected a supermassive black hole from when our universe was less than 600 million years old. In universe terms, it's just a baby. This is the most distant actively feeding supermassive black hole ever observed. It's located at the heart of its host galaxy called Sears 1019. The black hole is surprisingly small and not massive at all. It's actually one of the smallest found in the early universe. It's equal to approximately 9 million suns. It might sound like a lot, but in reality, supermassive black holes tend to grow to billions of times the mass of our star. There's another unusual thing about this find, and scientists are having a hard time trying to explain it. You see, it's supposed to take way longer than 600 million years for a supermassive black hole to grow to its full potential. The development happens when a black hole either feasts on surrounding matter or merges with a larger black hole. Even black holes similar to the one at the center of our Milky Way galaxy, which is almost 4.3 million times the mass of our Sun, are supposed to be seen in the more recent universe. Actually, scientists have long suspected that supermassive black holes probably existed in the early universe. But this theory has been proven only thanks to the JWST and its infrared eye. It's shown that the black hole Sears 1019 is actively munching on all the matter it can lay its hands on. Such feeding black holes are usually surrounded by swirls of gas and dust, falling inside them, called accretion disks. The gravitational force of a black hole heats this matter, and it makes the disk shine. And that's not all. Extra strong magnetic fields produced in this process channel the matter to the poles of the black hole. From time to time, this matter is released into space in twin, powerful jets. They move at a speed that is close to the speed of light, which generates incredibly bright light. Astronomers were watching the galaxy hosting the unusual old black hole as part of the Cosmic Evolution Early Release Since survey. They saw the galaxy as it was when our 13.8 billion-year-old universe was just 570 million years old. Besides the super old black hole, scientists spotted two other ones. Those probably appeared 1 and 1.1 billion years after the Big Bang. They also discovered 11 ancient galaxies that existed between 470 and 675 million years after the beginning of cosmic history. Now, how about having a look at the biggest black holes astronomers have found so far and finding out what would happen to Earth if one of them was to enter the solar system? NGC 6166 is a monster that has grown to have a mass of 30 billion solar masses. It's an elliptical galaxy that has an active nucleus at the center. It's also one of the most luminous sources of X-rays. The galaxy's supermassive black hole powers two symmetric radio jets in the opposite direction, which is the result of the infall of gas into its center. Another peculiar thing about NGC 6166 is that it shows a blue shift, which means it's moving towards us. Is it time to pack up and move out of our solar system? The next supermassive black hole is located in the constellation of Draco, approximately 10.4 gigalight-years from us. The mass of this supergiant is more than 30 billion solar masses. Besides being incredibly massive, the black hole is also really big. If it replaced our Sun, the diameter of this hole would extend to the orbit of Pluto. The next black hole is one of the most interesting on our list. It has a mass of 40 billion solar masses and is actually a blazar. It's the most energetic of all quasars, super bright distant objects. The blazar's luminosity is 300 trillion times that of the Sun, and more than 25,000 times as great as the luminosity of all 100 to 400 billion stars of the Milky Way galaxy combined. But since the distance to this quasar is about 12.1 billion light-years, we can't see it directly. But we know that the central black hole of the quasar consumes huge amounts of matter. About 4,000 solar masses of material every year. IC 1101 is a supergiant elliptical galaxy. It's the most massive known galaxy so far. Since this galaxy is elliptical, it isn't filled with gas. That's why the star formation in that region is very low. As for the black hole at the center of this galaxy, it lies in the mass range of 40 to 100 billion solar masses and emits clear radio signals. But wait for this champion. Astronomers have discovered a gravitational space wonder that has grown to really unimaginable proportions. The black hole I'm talking about is TON 618, and it's a mind-boggling 66 billion solar masses. Yep, we've got another ultra-massive black hole here. Imagine gathering all the stars in our home Milky Way galaxy and squishing the matter they're made of into one black hole. And it still won't be enough to create a TON 618. If this monster of a black hole replaced the Sun, its radius would be more than 40 times the size of Neptune's orbit. You know that black holes are incredibly dense, but it doesn't mean they're some kind of space predators roaming galaxies and munching on everything they come across. TON 618, for example, still has a whole galaxy filled with stars and other stuff happily orbiting it without getting pulled inside. So the perception of black holes as giant vacuum cleaners is wrong. In reality, it's incredibly hard to grow a black hole. Try and you'll see. And now, what if a supermassive black hole, like the one that dwells at the center of our home Milky Way galaxy, moved a bit closer to our solar system? The answer is simple. We'd be doomed. The distance between this huge thing and Earth would be several dozens of light years, and still, it would wreak total havoc on our planet. Earth, along with other objects making up the solar system, would be tugged into the black hole's orbit and doomed to spin around it for eternity. But you can relax and breathe out. Such massive black holes stay away from us at the moment.
Stellar mass and intermediate mass black holes form when huge stars can't support nuclear fusion anymore and collapse, unable to withstand their own gravity. But it's not so clear with supermassive black holes. The mechanism of their formation is still unknown, since there seem to be no stars large enough to directly collapse into such a giant black hole. Nearly every large galaxy has a supermassive black hole at its center, and our Milky Way isn't an exception. We've got Sagittarius A, which is pronounced Sagittarius A star. This space monster is mostly dormant and rarely wakes up to munch on gas and dust, and still, its mass is millions of times that of the Sun. To be precise, almost 4.5 million times. There are still lots of mysteries surrounding this black hole, but one of the most recent discoveries can also be the most exciting. But we'll get there later. Right now, imagine a distance of 14.6 million miles. It's like about 61 distances from Earth to the Moon. That's the diameter of our supermassive black hole. Of course, it will look tiny compared to the Milky Way itself, which is 100,000 light-years wide and 1,000 light-years thick. But it's still impressive. At the same time, Sagittarius A is dwarfed by a disk of gas surrounding it. It extends for a whopping 5 to 30 light-years and occasionally feeds the black hole. When it happens, faint flashes of X-rays are produced. The disk, known as the accretion disk, is also responsible for X-ray emissions triggered by friction. This friction can make the temperatures inside the disk go as high as 18 million degrees F. And now the coolest part. The supermassive black hole at the heart of our galaxy is not just spinning, it's doing so at almost maximum speed, dragging everything close to it along for the ride. Scientists have calculated the rotational speed of Sagittarius A with the help of NASA's Chandra X-ray Observatory. Normally, the spin speed of a black hole is given a value from 0 to 1, with 1 being the highest rotational speed. Speaking of our supermassive black hole, its rotational speed is between 0.84 and 0.96. That's close to the top limit, defined by a black hole's width. Now, the spin of a black hole is very different from that of other space bodies. Solid objects, like planets, moons, or asteroids, have physical surfaces. But black holes are regions of space-time surrounded by an outer, non-physical surface. This surface is called the event horizon, and even light can't escape beyond it. The rotation of a planet or a star depends on the distribution of its mass. At the same time, the rotation of a black hole is governed by its angular momentum. The extreme gravitational forces next to a black hole cause space-time to become slightly curved and twisted. It forms what we know as the ergosphere. This notion is unique to black holes and never occurs around relatively solid space bodies like planets or stars. In other words, when black holes spin, they twist up the very fabric of space-time, dragging along the ergosphere and everything it contains. This phenomenon is known as frame dragging. Come to think of it, the name does make sense. Thanks to this dragging, we can observe weird visual effects around black holes. The theoretical maximum speed of a black hole is determined by how it grows after feeding on matter. As something falls into a black hole, it increases its spin. Plus, we should take into consideration the mass of a black hole. The more massive it is, the higher its gravitational pull is. And this makes it more challenging to increase the speed of the spin. Let me illustrate this idea. Our relatively not-so-heavy supermassive black hole, whose mass is equivalent to around 4.5 million suns, has a spin between 0.84 and 0.96, which is very fast. At the same time, a much heavier supermassive black hole at the heart of galaxy M87, which has a mass of 6.5 billion suns, is spinning just as fast, between 0.89 and 0.91. The solution to this mystery? This black hole is also feeding very rapidly, which allows it to increase its speed.
Black holes are terrifyingly dense space objects, pulling inside everything that comes too close. Nothing can escape their clutches, even a beam of light. At the same time, black holes are some of the most mysterious objects in the universe. According to their mass, black holes are usually divided into 3 categories. Stellar black holes have a mass from a few to hundreds of times the mass of the Sun. Intermediate black holes should range from 100 to hundreds of thousands of times the Sun's mass. Scientists are now actively hunting these missing link black mysteries. But the real behemoths of the cosmos are supermassive black holes. They have hundreds of thousands to billions of times the mass of our Sun. Most supermassive black holes lie in the centers of their home galaxies. You can probably say that they sit in the gravitational driving seat. Meanwhile, hundreds of billions of stars, planets, and moons orbit them. Let's have a look at the biggest black holes astronomers have found so far. NGC 6166 is a monster that has grown to have a mass of 30 billion solar masses. It's actually an elliptical galaxy that has an active nucleus in the center. It's also one of the most luminous sources of X-rays. The galaxy's supermassive black hole powers 2 symmetric radio jets in the opposite direction, which is the result of the infall of gas into its center. Another peculiar thing about NGC 6166 is that it shows a blue shift, which means it's moving toward us. The next supermassive black hole is located in the constellation of Draco, approximately 10.4 gigalight years from us. The mass of this supergiant is more than 30 billion solar masses. Besides being incredibly massive, the black hole is also really big. If it replaced our Sun, the diameter of this hole would extend to the orbit of Pluto. This S5 Theora 1481 is one of the most interesting black holes on our list. It has a mass of 40 billion solar masses and is actually a blazar, the most energetic of all quasars, which are super bright distant objects. The blazar's luminosity is 300 trillion times that of the Sun and more than 25,000 times as great as the luminosity of all 100 to 400 billion stars of the Milky Way galaxy combined. But since the distance to this quasar is about 12.1 billion light-years, we can't see it directly. But we know that the central black hole of the quasar consumes huge amounts of matter, about 4,000 solar masses of material every year. IC 1101 is a supergiant elliptical galaxy. It's the most massive known galaxy so far. Since this galaxy is elliptical, it isn't filled with gas. That's why the star formation in that region is very low. As for the black hole at the center of IC 1101, it has a mass of 40 to 100 billion solar masses and emits clear radio signals. Recently, astronomers have discovered a gravitational space wonder that is swollen to really unimaginable proportions. The black hole I'm talking about is TON 618, and it's a mind-boggling 66 billion solar masses. The thing is so massive that astronomers had to think of a new term to describe it. They came up with an ultramassive black hole. Imagine gathering all the stars in our home Milky Way galaxy and squishing the matter they're made of into one black hole, and it still won't be enough to create a TON 618. If this monster of a black hole replaced the Sun, its radius would be more than 40 times the size of Neptune's orbit. You probably know that black holes are made of matter packed together as densely as possible. And still, it doesn't mean that black holes are some kind of space predator, roaming galaxies and munching on everything they come across. TON 618 still has a whole galaxy filled with stars and other stuff happily orbiting it without getting pulled inside. What I want to say is that the perception of black holes as giant vacuum cleaners is wrong. In reality, it's incredibly hard to grow a black hole. Try to do it and you'll see.
A black hole is an eerie place where those laws of physics we studied at school stop working. If a massive star runs out of its fuel, it sometimes becomes super dense and buckles under its own weight. collapsing inward and bringing space-time along. As a result, the gravitational field of this new object gets so strong that nothing can escape it, not even light. That's how a black hole is born. The black holes closest to our planet are called Gaia BH1 and Gaia BH2. They were discovered thanks to the data collected by the European Space Agency's Gaia spacecraft, hence their names. Both are about 9 to 10 times more massive than our Sun and are located a mere 1,560 and 3,800 light-years away, respectively. In cosmic terms, they're situated in Earth's backyard. And there's something seriously wrong about these black holes. So, should you pack your emergency bag? Let's find out. The remarkably close black holes are likely to represent a previously unknown category of these mysterious objects. What sets them apart from others is that they're orbited by stars at much greater distances than scientists have observed previously in other black hole companion star pairings. Normal black hole companion star systems are known as X-ray binaries. They are usually bright in radio and high-energy X-ray emissions. They swallow matter and emit powerful bursts of energy, which makes them pretty easy to spot. Now, why did it take astronomers so long to spot these massive black holes residing right inside our home Milky Way galaxy? All because they're almost invisible. In the past, astronomers spotted black holes by looking for the remnants of their meals. The thing is that when a star or even a cloud of interstellar gas is pulled into a black hole, it leaves behind a trail of electromagnetic radiation. And scientists use it to detect the presence of a black hole. But unlike other holes discovered before, Gaia BH1 and BH2 are pitch black. They don't seem to be snacking on anything at the moment. This makes them inactive, or dormant. So astronomers had to use another method. They tracked the movement of two companion stars orbiting these cosmic monsters. The stars, similar to our Sun, wobbled a bit while traveling through space. To researchers, it was a sign that something with a lot of gravity, like another star, was tugging on them. Interestingly, when they examined the area with the help of telescopes, they didn't find anything emitting radiation. So the whole situation only made sense if there was a black hole involved in the process. Luckily, Gaia is perfect for spotting invisible black holes. Thanks to its state-of-the-art equipment, it can accurately measure the motion and position of billions of stars. No other instrument is capable of such precision. Gaia's observations were backed up by the data received later by other observatories. For instance, NASA's Chandra X-ray Observatory, as well as the South African Meerkat Radio Telescope, revealed no visible light coming from Gaia BH2. So even though they detected nothing, it was still valuable information. It told astronomers a lot about the environment around the black hole. A lot of particles are coming towards it from the companion star in the form of stellar wind. But the researchers didn't spot any radio light. It means that the black hole doesn't have much of an appetite, and not many particles cross its event horizon, or the point of no return. Unfortunately, it's still unclear why that is. Anyway, should we be worried about those mysterious black holes lurking in the darkness of space so close to our planet? I've got some good news. There's absolutely no reason to worry. First of all, these black holes are sleeping at the moment. And it doesn't look like they're going to wake up anytime soon. Secondly, they're still too far away to affect our life. And it's not like black holes know how to travel.
The James Webb Space Telescope has recently discovered the oldest black hole ever found. It's an ancient monster as massive as 1.6 million suns, and it's lurking 13 billion years in the past at the center of an infant galaxy. This supermassive black hole appeared a mere 440 million years after the beginning of the universe. But it's just one of the countless black holes that inflated to terrifying scales during the dawn of the cosmos. It's the period about 100 million years after the Big Bang. That's when the young universe started to glow for 1 billion years. This discovery of the universe's oldest black hole can provide astronomers with the answers to some vital questions. For example, how could these space whirlpools balloon in scale so fast after the universe began? Or how did they appear in the first place? You see, black holes in the early universe couldn't grow as quietly and steadily as many modern black holes do. They were bound to experience some peculiar formation and growth. At the same time, closer to the present day, black holes are believed to be born from the collapse of ginormous stars. They grow by munching on gas, dust, stars, and other black holes non-stop. The friction created in the process makes the material, spiraling into a black hole, heat up, and it emits light that can be detected by our telescopes. To spot the oldest black hole, scientists used two infrared cameras, the JWST's mid-infrared instrument and near-infrared camera. They used the camera's built-in spectrographs to break down the light it had been recording into its component frequencies. While examining the results, they discovered unusual spikes among certain frequencies. It could only mean that the hot material around a massive black hole was beaming out faint traces of light. One of the most popular explanations for how ancient black holes grew so rapidly is that they appeared after sudden collapses of colossal gas clouds. Or they could form as a result of merges between clumps of stars and black holes. There's also a possibility that some of the oldest black holes could have been seeded by hypothetical primordial black holes. Those are believed to have appeared moments after the universe began, but their existence hasn't been proven yet. In any case, this most recent finding of the ancient black hole is extremely important because the formation of galaxies and the appearance of black holes go hand in hand. Every normal-sized galaxy that we know of has a black hole at its center. But even though such black holes are massive and can weigh millions and billions of solar masses, they are still tiny in comparison with their home galaxies. A supermassive black hole usually reaches less than 1% of the mass of a regular-sized galaxy and has a volume that is billions of times smaller. And still, somehow, supermassive black holes can influence galaxies, controlling the formation of stars for billions of years. The thing is, black holes exert an enormous gravitational pull on their surroundings. Any gas, dust, and stars that come too close to a black hole find themselves trapped. A lot of material crams into the space around the black hole and heats up, because that's what materials do when compressed. Soon, everything around the black hole flattens into a thin disk, which is called the accretion disk, and starts swirling around the black hole. Astronomers believe that this process is behind the mysterious relationship between black holes and their host galaxies. It's a connection between the mass of the supermassive black hole and the velocity dispersion of the gas in the galactic core. This cycle also controls the rate of star formation, which is a crucial element of the evolution of galaxies. If this delicately balanced process goes off kilter, the outflows from black holes can get too strong, not only heating the gas in a galaxy, but also removing it altogether. And then, the formation of stars doesn't simply slow down, it stops completely. Major galactic merger events can lead to such dramatic consequences because too much material falls into the central black hole too fast.
You might think falling into a black hole is as easy as falling into a giant pit, but boy, is it a whole different ballgame. To actually fall into a black hole, you would need some incredible luck and a dash of wizardry. Moreover, if you were watching something fall into a black hole, you wouldn't even see it. Why? Well, let's try to understand the magic of physics. Falling into a black hole is really tricky. First of all, to even have a chance of doing this, you would need to aim perfectly and start your journey from very far away. It's like trying to hit a tiny target from a long distance. That's because black holes exist within galaxies, which are filled with other objects like stars, planets, and gas clouds. These objects have their own gravitational forces that can influence the path you need to take. It's like you have to carefully navigate through the room, avoiding bumping into others or getting pulled off course by their movements. In a similar way, when falling into a black hole, you need to navigate through the influences of other celestial objects, As you get closer, things get even more complicated. Making even the tiniest change in direction would require a tremendous amount of energy that you wouldn't be able to generate. It's like trying to steer a spaceship with no fuel left. This is because the black hole's gravitational pull is immensely strong. Once you pass the point called the event horizon, there's no coming back. You wouldn't be able to control anything. Now, even if you somehow manage to get on the right path and avoid all the obstacles, there's still a dangerous situation waiting for you. The intense heat and energy around the black hole, called plasma, would fry you as you get closer. So, you would need some impossibly strong protection to get even close to it. But not only is it nearly impossible to fall into a black hole, it's also impossible to see someone falling in it. Why? Let's find out. Imagine you're standing far away from a black hole, watching something getting closer and closer to the event horizon. As this thing, let's say it's a spaceship, falls into the black hole, two very strange things start happening. First, the color of the spaceship will change. You see, the gravity near a black hole is incredibly strong, much stronger than anything we experience here on Earth. This intense gravity affects everything around it, including light. Now, light has this fascinating property where it carries energy. But when light gets close to a black hole, the powerful gravitational pull starts sapping away its energy, kinda like stealing it, making light weaker. And you know how when you look at a beautiful sunset, the sun appears to be this warm, reddish-orange color? Well, that's because when sunlight travels through our atmosphere, it scatters and loses some of its higher energy bluish colors, leaving behind the redder ones. So when light loses energy, it tends to shift towards the red end of the color spectrum. The same thing happens near a black hole. The light from the spaceship loses energy due to the black hole's strong gravity. So, the spaceship, which initially had its own color, starts looking redder and redder as it gets closer to the black hole. It's as if the black hole is casting its magical spell, changing the color of the spaceship itself. The second weird thing is related to time. According to a theory of general relativity, gravity can mess around with time itself. And it works in a very strange way, because none of you, not people on board a spaceship, will feel this change. For you, an observer in this scenario, time is flowing just like it always does. You're just sitting there, sipping your space lemonade and watching the spaceship's journey. For people on a spaceship, things are the same. Their watch ticks away at a regular pace, and they go about their day as usual. But, objectively, for you, it would be like watching a spaceship fall in slow motion. It will seem to you that it's been falling into a black hole for weeks or even years. You might turn 80 and the spaceship is still out there. Crazy, right? Now, if time slows down for the spaceship, it means the light it emits also slows down. So, imagine someone on that spaceship flicking a flashlight on and off. But because time is moving so slowly, the light coming from the flashlight also moves in slow motion. It takes ages for each burst of light to reach your eyes. You'll be watching a spaceship as if you're watching a video in super slow motion. And when light takes longer to reach your eyes, it becomes weaker and dimmer, just like a fading star. So, as the spaceship gets closer and closer to the black hole's event horizon, not only does it start looking redder, but it also appears dimmer. So, it becomes harder and harder to see the spaceship as it gets closer to the black hole. It slowly fades away, like a disappearing act on the grandest stage of the universe. Pretty mind-boggling, isn't it? But that's all about you, the observer. And how are people on board doing? What do you actually experience when you fall into a black hole? As you get closer to the black hole, something really weird starts happening. The gravity near the black hole is so powerful that it stretches and warps everything around it. So the difference in gravitational pull between your head and feet becomes significant. This difference creates a tidal force, which stretches your body like a long, thin shape. It's a process that's scientifically called spaghettification. Essentially, you would be stretched into a human noodle. Being turned into spaghetti might sound fun for a pasta lover, but it's definitely not so great for an astronaut. Meanwhile, colors around you begin to warp and distort, creating a dazzling light show. It's like riding a roller coaster through a rainbow tunnel. Twists and turns, flashes and sparks. It's an exhilarating, mind-bending experience. And then, what happens to you depends on the type of black hole. First, we have classical black holes. These are black holes that exist forever. If you fall into this black hole, it would take an incredibly long time to reach the center. The center would keep getting closer and closer, but you would need an almost infinite amount of time to reach it. So it would feel like your journey would never end. And then we have evaporating black holes. These black holes can evaporate over time due to a process called Hawking radiation. It's just like the ice cubes melting away. These black holes have a limited lifespan, and it's basically impossible to fall into one of them. As you approach the evaporating black hole, you find yourself hovering near its edge, the event horizon. It's like being stuck at the entrance of a super cool amusement park. But guess what? This amusement park is shrinking. The black hole is evaporating, and as it does, the event horizon gets smaller and smaller. So you stay right at the edge, tracking its every move, but you will forever stay in this event horizon without ever crossing it. But remember, once you pass the point of no return, there's no way back. You're on a one-way ticket to the mysterious heart of the black hole, the singularity. At the singularity, everything goes bonkers. Our current understanding of physics goes haywire, so it's a bit like entering a magic show. What happens once you reach the singularity? Is there anything on the other side of a black hole? We have no idea. It's a big mystery for us, but maybe we'll figure this out someday. So, my friend, it's best to admire black holes from a safe distance and let your imagination soar with the incredible wonders they hold. Just remember to keep your pasta on your plate and not near these cosmic spaghetti makers.
Okay, here's the deal. Something is bound to happen that can affect everything we've ever known about space and time. You've heard about black holes, right? That denser-than-life type of phenomenon that usually exists in the center of galaxies? Two of them, located 9 billion light-years away from Earth, are expected to collapse into each other. And my oh my, I do not want to be around to see that. Let's get one thing straight. Black holes are the most powerful things in the entire universe that we know of. If they decided to go all Revenge of the Sith on us, we'd be doomed. A black hole was once a massive star that went supernova, meaning that the star collapsed onto itself, and the sheer magnitude of the explosion created a black hole in its place. Oh, by the way, black holes do not pull things inside like a vacuum cleaner. That's just a popular myth. Say we were to replace our sun with a black hole at the center of the solar system. Not much would change, except that maybe we'd all freeze. Yup. But black holes can do something much worse than vacuum stuff. They can delete the universe itself. If a black hole was to follow a normal timeline, it would go from its creation to total disappearance. But this process is very, very slow. I'm talking about billions and billions of years before a black hole loses its mass entirely. That happens because they're constantly losing their mass every single second. Black holes radiate their mass away, like a boiling teapot loses its water as steam. Yet things rarely go as planned, both in our lives and apparently in the universe itself. So it wouldn't be that much of a surprise to find out that two black holes are en route to collapse. That's what scientists have found out recently. And let's just say that this is one of the reasons why the scientific community is freaking out just a little bit. The first question that comes to mind is, what does that mean for us humans? Total annihilation? No need to be this dramatic. The best case scenario, we'd be in for an interstellar type of experience. Roll me in, please. Let's rewind a little bit to understand how this would happen. 45 years ago, a group of scientists began noticing a weird behavior coming from a galaxy far, far away. The galaxy is found 9 billion light-years away, and its scientific name is a mouthful, but let's just call it Super Far Away Galaxy. You might be asking yourself, well, how did scientists observe this black hole so far away if it doesn't emit any light? Good question. That's because black holes gather disks of gas around them and they emit some of this material into space. These jets can be detected from a distance of millions of light years. Now, if these hot gas jets are directed towards space, then scientists give these black holes a special name – blazars. A particular blazar has been gaining worldwide attention recently. Long name, but let's just call it Andy. Imagine you're a scientist at Caltech and you're looking at a blazar in your radio telescope and you notice its strange behavior. Its brightness goes on and off, like the ticking of a clock. At first, you don't understand what's happening over there in a distant corner of the galaxy. But then, you realize there must be another black hole circling the first one. In other words, scientists discovered that Andy was being orbited by another blazar, Gomer, and the regularity of their twinkling can only mean they are close to a total collapse. It gets worse. Each of the two blazars is estimated to be a few 100 million times the mass of our Sun. Have you seen our Sun? It's huge. It's already 333,000 times the mass of our Earth. This means we're destined to face something out of our league. Now, this is not the first time scientists have detected something like this. In September 2015, the LIGO Observatory detected a collision of two black holes. Each of them was as heavy as 30 suns, and an equivalent of 3 solar masses was released once they crashed into each other. And guess what? This gravitational wave passed through Earth at the speed of light. But we really weren't affected by it. Maybe you were sleeping and felt something weird in the air, but nothing significant happened to us as a species or to our planet. But that's because the blast was weak. The thing is, the expected collision between Andy and Gomer will send unprecedented gravitational waves throughout galaxies, and they will reach the solar system. But what is this shock wave actually capable of doing? Well, it could stop our Sun from releasing gas for a few minutes, which means it would stop heating the solar system. So, let's say you were going about your summer day and, out of the blue, the atmosphere froze for a few seconds. Doesn't sound too nice, huh? But that's actually a better possibility than the next one. In one of the worst-case scenarios, a blast from the collision between Andy and Gomer could break bonds between atoms and make everything disintegrate. You, me, your cat, we'd all turn into flying particles floating in the vacuum of space. This may sound scary, but scientists say that an atom is made out of 99% empty space. This means that everyone on this Earth, all 8 billion of us, and everything that exists, planets, objects, animals, are all made up of 99% empty space. So perhaps all that Andy and Gomer would do is separate all of our atoms and desolidify us. Then again, the blast could mess with the fabric of space and time as we know it. You remember Albert Einstein, right? Crazy hair? He's the name behind the theory of relativity. Einstein discovered that time is relative. It's always dependent on the observer. This would mean that time is not the same throughout the cosmos. Why, though? Well, because Einstein's theory of relativity is also a theory of gravity. Einstein discovered that gravity is the effect that objects have on the fabric of space-time. Every object that has a mass, including you, me, your cat, and our planet, creates a warp or a distortion in the fabric of space-time that causes it to bend. The bigger the mass, the bigger the gravitational force, and the bigger the distortion on the fabric. It may sound complicated, but hey, this is what creates different perceptions of space and time throughout the cosmos. This is why you'll age differently on Earth and on Jupiter. This is why time passes completely different for astronauts on long missions and for people that remain on Earth. And this is why a collision of two mega blazars could mess with our perceptions of space and time, due to the sheer force of its gravitational shockwaves. Got it? Not to mention that black holes are already a huge warp in the fabric of space-time. You remember that Interstellar scene, right? Where the lead character bends the space-time continuum through a black hole? Now, don't try this at home, though. As far as we know, anyone who chooses to go inside a black hole has no guarantee of making it home again. Scientists say that this blazar explosion will happen in approximately 10,000 years. But wait a minute. If this blazar lies 9 billion light-years away from Earth, It means that these two black holes should have already collided long before our solar system and home planet were born. You see, the solar system was born around just 4 billion years ago. And since it takes us 9 billion light years to receive the light emitted from the blazars in the first place, this means that the collapse of the two blazars already took place, and it'll reach Earth 10,000 years from now. This means the shock waves are already making their way through the galaxies at this very moment. But still, it's not something even your great-great-great-great-great-great-grandchildren will be around to see.
Imagine simultaneously being born, growing up, and getting old somewhere out there in the universe. Sounds bizarre and unrealistic. And still, according to the block universe model of the world, that's exactly what happens with you, me, and other living beings on our planet. It's as if someone drew pictures about every moment of your life and then just piled them one on top of another, creating a giant block of all things that ever happen at any time and at any place. The future, present, and past exist at the same time and are equally real. The block has 4 dimensions. 3 of them are spatial. It's length, width, and height. There's one more, time. To make it easier, let's picture our world as a cuboid, which is basically a 3-dimensional rectangle. Its height and width represent 2 of the 3 spatial dimensions of the universe. As for the 3rd spatial dimension, we'll replace it with time. At one end of the cuboid, we'll drop the Big Bang. And at the other, there will be the end of the universe. Let it be a big crunch. Our cuboid is filled with every single event that ever happens. Even this moment, when you're watching this video, exists somewhere in the block. Now, we perceive today as the present, yesterday as the past, and tomorrow as the future. From this perspective, it seems that time passes. But in the block universe, time doesn't flow. There's no specific present moment since the notions of the past and future are relative. You see, we are always located wherever we are, which means that everyone remains in the present. But the block universe theory doesn't deny the notions of earlier than and later than. These relations remain no matter what and regardless of where anyone is located. For example, Molly the mammoth is located earlier than Marcus the tiger. This relation between Molly and Marcus will remain unchanged regardless of whether you're located later than Marcus or earlier than Molly. This way, in the block universe, now is any time you are located at. Past is any time or events that are earlier than your location, and future is any time or events that are later than your location. It sounds like in the block universe, we could travel in time since it's just another dimension. Well, it could be true, but of course, things just have to be more complicated than that. Traveling in time is way more difficult than traveling in space, but it's not impossible if you travel very, very fast. Traveling at extremely high speeds results in time dilation. We can travel into the future at a reasonable percentage of the speed of light, and to get to the past, we can use wormholes, shortcuts through space-time. But if we can travel in time in the block universe, can we change the past? Not really, because if you do, it'll create a contradiction. Keep in mind that, in this universe, the past is the same as the present or the future. What is past to you is future to someone else. And when traveling to the past, you're going to someone else's future. In the past, you'll act just like you do in the present, but you won't be changing the past. All your actions are already predetermined in the block universe. At the moment of the Big Bang, it's already clear that at one point, you'll travel to the relative past. Just like what you do tomorrow makes tomorrow the way it is and has always been, what you do in the past makes it the way it is and has always been. The events in the block universe do not change. As a time traveler, you don't suddenly appear in the past. It's always been the case that you're located in the past. And nothing a time traveler does can change anything in the block. Instead, whatever you do at any time makes that time the way it is.
Imagine a world of seething hot metal where iron and nickel dance in a fiery inferno. This is the inner core, the heart of our planet. But what if this very heart was changing? The latest research suggests that the Earth's inner core may be slowing down and even reversing its rotation. Is this a sign of the end of times? Will the Earth come crashing down on itself? Let's find out. Imagine you have a giant onion, and every layer represents a different layer of the Earth. The center of this onion, the part you can never reach, represents Earth's core. It's like a mysterious land that no one has ever set foot on, yet scientists have been trying to uncover its secrets for centuries. Imagine diving deep into the center of the Earth, beyond the crust, the mantle, and finally 1,800 miles below the surface where you'd reach the inner core. It's a ball of seething hot metal made up of solid iron and nickel, and it's so hot it glows a brilliant white. It's also surrounded by a liquid outer core. This mysterious place is unlike anything else on our planet. And get this, it's spinning on its own axis. The inner core is like a fire tornado that's constantly swirling, generating heat and energy from the inside out. But why is it so important to study this little piece of the Earth? Well, it's responsible for creating our magnetic field. This magnetic field is important to study because it protects us from harmful radiation from the sun. It's created by the movement of molten metal in the Earth's outer core and the spinning of the Earth. These movements generate electrical currents, which then create the magnetic field. It's like a shield that protects us and helps us keep our planet healthy and safe. But there's still so much we don't know about the inner core. For example, how did it form? Scientists believe it started to solidify about 1 billion years ago. But why did this happen? What was the trigger? Or, for example, what about the inner core's crystal structure? It's thought to be a type of iron called hexagonal close-packed iron, but we still don't know if it's actually the case. In other words, we may have many theories, but unfortunately, there's no way to confirm them, at least for now. So how do scientists study the inner core if no one can go there? They use seismology. Seismology is like a sonic scanner for the Earth. You send sound waves through the Earth and measure how they bounce back to see what's inside. That's basically how we discovered the inner core way back in the 1930s. Imagine you're listening to the sound waves with your special seismology machine. Suddenly, you hear a strange sound like a ping. It's different from the other sounds you've been hearing, and you can't explain why. You keep listening and you hear the ping again and again. You start to realize that this ping is happening every time the sound wave hits the Earth's center. You study the data more and more, and finally, you figure it out. The Earth has a solid core. This discovery was a big breakthrough and helped us better understand what's inside our planet and how it works. Right now, scientists also use something like this to study what's inside our planet. When earthquakes occur, waves travel through the Earth and bounce off different layers, including the inner core. By studying these waves, scientists can learn about the inner core's properties, such as its density and temperature. They're basically solving a mystery by piecing together tiny clues. And every new discovery brings us one step closer to understanding it. The inner core is a unique and fascinating part of our planet. It's a place where the laws of physics work in different ways than they do on the surface. And it's a place where scientists are still trying to unravel its many mysteries. And here's one of them. For some reason, the heart of our planet is about to stop spinning. A new study about this was published in Nature Geoscience. It was made by the researchers at Peking University in China. It has revealed a huge twist. The scientists found that the inner core spin rate has slowed down significantly. It's something that no one expected, but according to the results of their study, the slowing down began all the way back in 2009. And that's not all. Their results also suggest that the inner core may be reversing its rotation. That's right. This hot ball of iron and nickel that has been spinning around for millions of years may be slowing down and changing direction. It's like when a spinning top starts to slow down, except this is happening in the center of our planet. Scientists have been puzzled over the discovery for quite some time now. So, what does it all mean? And why is this happening? Well, it turns out that there might be a larger pattern at play. The scientists believe that this change in the inner core's rotation may be due to the influence of Earth's mantle and the magnetic field of Earth's outer core. The mantle and the outer core are affecting the inner core, which is causing its spinning rate to slow down and potentially change direction. Before this study, scientists thought that the inner core was spinning faster than the Earth's crust. However, this new information suggests that the inner core may be slowing down due to the gravitational effect of the Earth's mantle and the magnetic field of its outer core. But here's where it gets even more interesting. When researchers took a closer look at data stretching all the way back to the 1960s, they discovered that the rotation of Earth's inner core was consistent from the late 1970s to the early 2000s. Before that, they found that another possible slowing down or reversal event may have occurred in the early 1970s. It's like the inner core spin is like a roller coaster ride, speeding up, slowing down, and possibly reversing course over a period of time. The researchers estimate that these switches occur every 7 decades or so, which is pretty wild. But why is it happening? Unfortunately, we still have no idea. The exact reasons for why the Earth's inner core sometimes stops and starts spinning in another direction aren't yet well understood. However, scientists believe that it may be due to complex interactions between the solid inner core and the surrounding molten outer core. A lot of different things can be at play here. The changes in the temperature, pressure, and composition of the core, as well as the movement of material within the core itself, and so on. Also, as we said before, the Earth's magnetic field and the gravitational forces from the surrounding mantle might also play a role here. We need further research to fully understand the mechanisms behind the inner core's rotation changes. So, is the world ending? Fortunately, no, not just yet. While the inner core is changing direction right now, it's not the end of the world as we know it. And even though findings may seem like a huge deal, life on Earth's surface hasn't been impacted much, if at all. In fact, it's just a fascinating part of the Earth's inner workings that we're learning more about every day. So, you can say with relief, nothing cataclysmic is happening. Moreover, according to Hervoya Kalsic, a geophysicist at Australian National University, the inner core is now more in sync with the rest of the planet than a decade ago when it was spinning a bit faster. All in all, this new study has added a strange twist to the story of Earth's inner core, and scientists believe that there's still much more to discover about this mysterious place. Who knows what other secrets lie in the heart of our planet? The possibilities are endless. So let's keep researching and enjoy our time on this amazing planet. There's this mysterious thing in space, an unusual spot that scientists haven't been able to explain for more than 15 years. There are different theories, and one of them says that maybe this is an imprint from a collision with a parallel universe. Is this true? Well, let's see. Take a look at this map. This is the map of our universe. Well, not really. This is actually the map of cosmic microwave background radiation, or simply CMB. Many billions of years ago, there was a Big Bang. It was so powerful that it created our entire universe. And, of course, such an event couldn't occur without leaving some consequences. And these consequences are literally everywhere. The Big Bang left electromagnetic radiation, which we know as CMB. We don't notice it in our daily lives, but it's literally here, under our noses. And if you had some kind of superhuman vision, you would see how everything around you shines with this dim light. This radiation is very important. If we hadn't discovered the CMB, we would never have found out about the Big Bang. Previously, scientists believed that the universe had always existed. There was no beginning and there was no end. It sounded pretty ridiculous to us now, but less than a century ago, people were absolutely sure of it. Stephen Hawking was one of the first scientists to guess that the universe did, in fact, have a beginning. The guy was so cool that he realized this as a student while working on his doctoral dissertation. But unfortunately, he had no proof. If there was such a strong bang billions of years ago, then where are the traces? Where's the proof? Laughed people who believed in the eternal static universe theory. But don't worry, they had the proof rubbed in their faces real soon. In 1965, astronomers Arno Pienzas and Robert Wilson discovered CMB, and that was the first grandiose proof of the Big Bang. It turned out that radiation was everywhere. We just didn't notice it. In fact, at first, Pienzas and Wilson themselves mistook it for the noise of a big city, or pigeons, or something else. For their discovery, which turned the world of science upside down, they received the Nobel Prize. Alright, so people learned that they were surrounded by electromagnetic radiation. Then they started collecting more data about it. They accumulated more and more info over the years until they made this very map. This is a map of CMB temperatures. But while creating it, scientists discovered something unusual. Let's take a look at this map. It looks like a large and diverse pattern of cold and warm places. But in reality, our universe is quite uniform. All temperatures on this map are close to -455 degrees Fahrenheit with very little difference. All temperature fluctuations between these places are small, and each tiny speck actually spreads over millions of light years. So everything in our world is pretty calm and stable, except for one point. This cold spot right here. Astronomers first discovered it in 2004. First, it looked like nothing unusual. It's just a region where the temperature is below average for a couple of microkelvins. But remember, we're not talking about a small area. This is a giant cold region. It's literally billions of light years in size. Wait, the scientists thought, this can't be true. The universe should be consistent everywhere. According to our standard model, this cold spot simply shouldn't exist. But it does exist though. This isn't just some mathematical error, it's right there. So what is this cold spot, and how did it appear? Astronomers have been trying to find the answers to these questions for years. Even now, we have only a few theories. So let's discuss them all. Theory 1. Cosmic texture. This idea was brought up at the end of 2007. Then scientists suggested that this cold spot could be the hills of space. In other words, it may be a bumpy region of the universe, just part of its texture. But that's a silly explanation, so this theory was quickly discarded. Theory 2. The supervoid. This hypothesis was considered the most plausible for a while. It stated that the cold spot was actually the so-called supervoid. It's a terrifying, dark place of our universe with almost no galaxies. And because it's an empty region with almost no stuff in there, it seems cold to us. However, this theory was refuted in May 2017. After carefully examining the cold spot, scientists found out that there were no signs of a supervoid there. Moreover, voids and supervoids, which actually exist by the way, are still very small in size. The cold spot is literally thousands of times bigger than them, so there must be some other explanation. And there is one, perhaps the most bizarre of them all. Theory 3. A parallel universe. This controversial idea was put forward by cosmologist and theoretical physicist Laura Mersini-Houghton. She suggested that the cold spot could be an imprint from the collision of our universe with a parallel one. Standard cosmology cannot explain such a giant cosmic hole, says Mersini-Houghton. This is the unmistakable imprint of another universe beyond the edge of our own. Her assumption is based on the theory of the multiverse. This theory says that there's actually an infinite number of universes like ours in the world. They constantly collide with each other, giving each other a push, which creates a new Big Bang. So maybe the cold spot is a bruise from such a collision. For quantum mechanics, such crazy theories are pretty common, but for standard physics and our simple understanding of the world, this is earth-shattering. Of course, we need strong evidence. And Mersini Houghton's team has begun to work on it. Professor Tom Shanks from the Center for Extragalactic Astronomy at Durham University also participates in this research. The craziest sounding of the exotic models for the explanation of the cold spot, the multiverse is actually the most standard in terms of our current model of the universe, he wrote in one of his works. So, what evidence do we need? Well, our cold spot is located in the southern hemisphere. According to Shanks, if there really was a collision between two universes, we should find another cold spot, and it should be in the opposite northern hemisphere. If astronomers actually found it, this theory would be confirmed, and it'd become the first proof of the existence of a parallel universe. But it's not that easy. To find a second spot, we need the latest, highly sensitive telescopes. We also need to find out some info about the nature of dark energy, how it affects space, and, in other words, there's still a lot of work to do. Not so long ago, scientists actually believed they had discovered the second spot. Researchers from New Mexico thought they had found it in the northern hemisphere. But unfortunately, this is likely to be a mistake. The map these researchers used had a high measure of randomness, so it's possible that their discovery is just an accident caused by other voids. So basically, we haven't found another cold spot so far despite careful analysis. But again, even the best modern equipment is not perfect, and it doesn't mean that there's no second spot. It just means that we haven't found it yet. But if one day we did find it, it could change the world of science forever. We'd confirm not only the theory of parallel universes, but also the famous string theory. It could explain everything that occurs in our world. But if this happens, we'll get even more questions than we already have. How did these two universes collide? How does it all work? So far, it's all just guesswork. We can't claim that the cold spot is a print from the collision of parallel universes. But we can't refute this either. Actually, we may never know the truth at all, but it's still interesting to strive for it.
How about going deep, deep into the past? To the times before humans existed, before the infamous asteroid hit Earth, wiping off 3/4 of life forms on the planet, even before the sun ignited or galaxies appeared in the darkness of the cosmos. So, before light could even shine, there was the Big Bang. It happened 13.8 billion years ago. But what was before that? Some scientists are sure that there was no before. Time started ticking as soon as the Big Bang occurred. We're unlikely to ever figure out what reality was like before that, if any. This is beyond human understanding. But there are those who disagree. Some unconventional scientists theorize that just a moment before the Big Bang, all the energy and mass of the nascent universe could be compacted into an insanely dense but still finite speck. Let's imagine it as a seed of a new universe. And this seed, a chunk of essential material, compressed and hidden in a protective shell, was created nowhere else but inside a black hole. Black holes spin incredibly fast, probably close to the speed of light. Such a spin can give the tightly compacted seed a ginormous amount of torsion. So the seed isn't just tiny and extra heavy, it's also compressed and twisted, which means that it can suddenly unspring with a big bang. Now, let's say you add up the energy and mass of all the particles the visible universe contains. And then you try to figure out the answer to the following question. How big could the event horizon of a black hole with the same mass be? The event horizon is the point of no return. Once you cross this invisible line, there's no way back, even for light. But let's get back to our question. Shockingly, such an event horizon would be very close in size to the actual horizon of the observable universe. There's also this idea that became well known thanks to Stephen Hawking. According to it, every time a black hole appears in our universe, it probably gives rise to a baby universe. But you would only be able to visit such a universe if you crossed the event horizon and plunged inside the black hole. And as you know, once you did it, you wouldn't be able to return. In other words, right now, we might be living in a baby universe. But if some outsider is observing us at the moment, our world looks to them like a regular black hole. So in short, there could be a very old mother universe that forged a seed inside a black hole. This seed had its big bounce all those billions of years ago, and as a result, our universe came into existence. But even though since then it has kept growing and expanding, we might still be hidden behind the event horizon of our home black hole. There's also another idea. According to string theory, there's a multiverse of universes. Imagine our universe as a soap bubble. This bubble keeps expanding, and we live on its surface. String theory claims that our bubble isn't unique. There might be other bubbles out there, and all these bubbles move around, collide, sprout, or bud baby bubbles. In short, live their life. If we follow this theory, we might suppose that black holes are one-way doors between universes. And if you accidentally tumbled down the black hole in our home Milky Way galaxy, you'd end up in another universe. Or rather, not you, but what's left of you after falling through the insane weirdness of the black hole. In this case, this second universe wouldn't be inside ours. It would exist separately, and the black hole would merely be the link connecting them, like a shared route between two aspen trees. Whatever the truth, the danger is still there, lurking in the shadows. What if the black hole we live in decides to collapse? What if it pulls us deeper inside? Or if our world is just a bubble among trillions of other bubbles? What if it bursts one day?
Imagine a powerful giant, like the sun, clashing with a tiny yet mighty opponent, a small black hole. The collision is imminent, and the fate of the solar system hangs in the balance. Will the sun be able to withstand the intense gravitational pull of a tiny black hole, or will it be swallowed whole? The answer lies in the forces at play in this mind-blowing cosmic collision, so let's break them down. First of all, what is a black hole? A black hole is a region of space where the gravity is so strong that nothing, not even light, can escape from it. Like a cosmic vacuum cleaner, it sucks up anything that gets too close. It's so massive that it warps the fabric of space-time around it. Black holes are one of the most scary and mysterious objects in the universe, a powerful force of nature that defies our understanding of physics, a true enigma of the universe. Black holes come in different sizes, from small ones that are only a few miles wide, to supermassive ones that are billions of times the mass of the sun. Most of them are formed by the collapse of massive stars. After the black hole is born, it starts to grow in size by eating everything in its path. And if two or more black holes collide with each other, they can merge into one enormous cosmic monster in a terrifying dance. But what about the smaller ones? The smallest known black holes are called stellar black holes. It's a type of black hole that weighs 3 to 10 masses of our sun, while being very small. It's like taking all the matter in the solar system and squeezing it into something the size of New York City. And yes, it's considered very small. Just for comparison, intermediate mass black holes weigh between 100 to 1,000 solar masses, and supermassive black holes weigh millions or billions of solar masses while being unimaginably huge in size. So, stellar black holes are basically nothing compared to their relatives. Imagine a massive star, bigger than our own sun and with a heart made of nuclear fuel, burning bright and hot. But as the star runs out of fuel, gravity takes over and starts to squeeze the star. The more it squeezes, the hotter it gets, until the star's core reaches a temperature of billions of degrees. Eventually, the core collapses under its own gravity. This creates a massive blast called a supernova. This collapse creates a singularity, which means a point of infinite density and gravity. This point is surrounded by an event horizon, the invisible line beyond which nothing, including light, can escape. And just like that, voila, a stellar black hole is born. Pretty mind-blowing, isn't it? Stellar black holes are the most common type of black holes we know of. These guys can be found all across our galaxy. So, what are the chances that such a little monster will come for our sun? And in that case, what will happen to us? Well, actually, the likelihood of the sun colliding with any black hole is incredibly small. It's almost impossible for it to happen. Even though stellar black holes are the most common type of black holes in our universe, they aren't common at all. The chances of the sun and some black hole crossing paths is so rare, it's basically like winning the intergalactic lottery. Only this win wouldn't be that pleasant. For 2023, the closest known black hole in our solar system is Gaia BH1. It's about 10 times heavier than our sun, and even this one is about 1,600 light-years away from us, which is a quadrillion miles. So, it's safe to say that our sun is not going anywhere anytime soon. But never say never, right? Just like with any astronomical event, we need to understand the different ways something like this could happen. For example, it would be possible if a rogue black hole passed through our solar system, much like a comet or asteroid passing by. Unfortunately, unlike comets and asteroids, black holes are invisible and can only be detected by their gravitational pull. So it's not like we'd see a big, ominous black hole hurtling towards us. Rather, we'd only know it was there if it caused some sort of disturbance in the orbits of nearby objects. So what now? We know that the sun is a massive, luminous star at the center of our solar system. It's about 4.5 billion years old and has enough fuel to last for another 5 billion years. This star is so big that it's hard to even comprehend its size. In fact, if you were to put all the planets in our solar system inside of it, there would still be room for more. And it's so massive that it contains almost 100% of the total mass of the solar system. So it's hard to imagine how some insignificant small black hole thousands of times smaller than this star can devour it. And you're right, it won't. Well, at least not completely. So imagine if a rogue black hole arrived in our solar system and has begun to approach the sun. As it gets closer and closer, the black hole's immense gravity will start to pull the material from the surface of the sun. The sun would start to get stretched and distorted. This is called spaghettification. Imagine a rubber band being stretched until it snaps. That's kind of what would happen to it. This gathered material will form a swirling disk around the black hole, called an accretion disk. As more and more material is pulled in, the disk will heat up and start emitting intense radiation. And as the sun gets pulled in, it would start to release massive amounts of energy in the form of light and heat. The sun would become much brighter and hotter than before. The sun's outer layers would be vaporized, creating a massive cloud of gas and dust that would expand outwards. It would be like a cosmic fireworks show, but with terrible consequences. Even though it would be one of the most spectacular views in the universe, we wouldn't be able to see it. As you might have guessed, the Earth would be in for a really rough time. The intense radiation and solar material would cause massive wildfires, and the intense heat would vaporize the oceans. The Earth would be bathed in a constant stream of high-energy particles, and the atmosphere would be ionized. In short, the chances of any life surviving would be close to zero. And this collision would have far-reaching consequences not only for the Earth, but for the entire solar system. The intense radiation and heat would vaporize everything in its path. All the planets would be destroyed. Now, the sun being a larger object than a typical star wouldn't be completely devoured by the black hole, but it would be significantly distorted and disrupted. The intense gravity of the black hole would cause the sun's outer layers to be pulled away, creating a massive blast called a tidal disruption event. But either way, in the end, the black hole would win. It would grow in size, and a new accretion disk would form around it. As we've seen, the collision of the sun with a black hole, whether it be a tiny or stellar one, would be an epic and catastrophic event. But thankfully, as we've already mentioned, the likelihood of such a collision happening is extremely low. However, that doesn't mean we should stop studying black holes and their potential impact on the universe. The more we learn about these mysterious objects, the better equipped we'll be to understand and predict their behavior. So, let's keep researching, exploring, and observing the depths of space. And who knows, maybe one day we'll come across a black hole that's just too curious and gets too close to the sun. Let's hope by that time, we will already be living on other distant planets. You know how galaxies have supermassive black holes in their centers? In most cases, we don't have to be afraid they'll come after us. They stay at the same spot for eternity, or at least until they start to evaporate and give the energy they have stolen back to the universe. But there's always that one rebel that spoils the statistics, like this invisible beast that ran away, moving farther and farther from its home galaxy. It escaped with style though, leaving a shiny trail of stars behind it, like a wake behind a ship. And it's moving really fast. If it was somewhere in our solar system, the moving black holes could cross the distance between our home planet and the moon in a mere 14 minutes. A regular spacecraft needs 3 days to do that. The unusual space wanderer weighs as much as 20 million suns and has left a trail of newborn stars 200,000 light-years long, which is twice the diameter of our galaxy. No one has definitely seen anything like that before. There are a few ways a supermassive black hole can run away from its home. One of them is when two galaxies come together in a big collision. As they hit each other, you get a pair of supermassive black holes that start dancing in circles around each other. If there's one more black hole that decides to join the party, it can give a big push to one of the dancers and kind of catapult it far away from the center of the galaxy. Another way is when the two dancers finally catch up with each other, align their moves, and become so compatible they merge at one point. This new black hole they create can get a push or a kick, and before it even knows it, it's somewhere far, far away from the safety of its home. This runaway black hole we're talking about is probably the result of many collisions of giant black holes. Their home galaxies probably merged around 50 million years ago, which brought these two together. Then, an intruder likely appeared, another galaxy with its very own giant space vacuum, and things quickly became chaotic. As one of those three tried to steal the moment from the other two, it ended up thrown out of the galaxy. The original pair may have stayed there, or maybe the guest took the place of one of them. Don't think it's always that easy to go after the rebel and talk it into going back home. It's generally really hard to detect black holes. Sometimes, they give away their current position when they eat large volumes of stuff they find on their way, such as gas and stars. When they're full, they become very bright. But the rest of the time, they just eat a normal amount and hide in the eternal shadows of the cosmos. They leave traces when they come closer to objects in space. We may not be able to see black holes directly, but special telescopes can catch what they do to their environment. For example, we can observe a star that makes circles around something we can't see instead of orbiting its binary companion star as we'd expect. Scientists can measure how fast that star is speeding up and calculate the mass of the object that's pulling on it. And when the mass is so big they can't match it with anything they know about, it means it's probably a black hole. Also, special X-ray telescopes can recognize radiation emitted by a star that has come too close to a black hole, which is now pulling it apart with its strong gravity. Black holes have an accretion disk, which is like a swirling thing that orbits them, like a whirlpool. When stuff from their surrounding falls into this whirlpool, it gets very hot and starts shooting out X-rays. Supermassive black holes have a mass of over 1 million suns, so it's not surprising they shoot out gas particularly far into space, sometimes even millions of light years away. Anyway, our rebellious black hole was hard to spot, considering how it kept moving faster and faster. But unlike others, it's never tried to hide, considering that shiny trail of stars. It doesn't gobble up stars that are ahead of it. Obviously not a fan of Pac-Man. Poor fella doesn't even have time to stop and grab a quick bite. Instead, it's just plowing into gas in front of it, which triggers the formation of new stars along its narrow path. The gas probably cools and forms a trail that's nearly half as bright as the galaxy itself. The black hole sits at the top of the column that stretches all the way back to its parent galaxy. It seems like this runaway wants to mark the way wherever it goes, in case it ever decides to get back home. And over there, at its tip, there's a glowing knot of ionized oxygen. It's probably there because it got shocked and heated from the black hole moving and hitting the gas. Or maybe this could be radiation coming from the accretion disk. This is not the only unusual black hole traveler that decided to take a different path in life. Astronomers have found another wanderer, a black hole, completely on its own for the very first time. Big stars can explode and turn into black holes, but in most cases, these black holes have star companions. When they come in a binary system, they interact with their partner so you can find them easier because of the light around them. That's why finding this solo traveler wasn't easy at all. It just didn't give off any light. But the Hubble Space Telescope did a pretty good job of finding how the gravity of this sneaky black hole bent light around it, similar to how a magnifying glass does. It's cool that we found something like this because it tells us there could be more of these loners that prefer traveling alone, hiding in the dark. These black holes sound scary, but the comforting thought is they're very far away. Take this lonely wanderer as an example. It's 5,150 light-years away from our home planet. But in 2020, scientists thought that they had found the closest black hole to Earth, only 1,000 light-years away from us. It was really big news until they realized they had actually fallen for an optical illusion. They thought there were 3 giant things over there. A big star making a circle around a black hole every 40 days, with one more star whose orbit went way farther. But it seems it was just a system of 2 stars orbiting each other closer than expected. But we've still got something cool to observe, because they're so close that one of the stars is pulling the atmosphere off the other. Yup, stars have their own vampires too. This vampire star is way bigger and spins faster than the other one. This results in an illusion that they're orbiting each other farther apart than in reality. Still, if I had to choose between these vampire stars and J114 in our galaxy, I'd definitely choose them. The latter one is a terrifyingly big black hole about 3 billion times heavier than our Sun. Our planet is not even a crumb in its morning bowl of cereal since it eats chunks of matter as big as the whole Earth every second. We're talking about the brightest and fastest growing black hole we've seen in the last 9 billion years. What's also fascinating is that this black hole devours matter so quickly that its boundary, which we call the event horizon, is really wide. You could easily fit all the planets of our solar system inside. The cool thing is also that its event horizon is so bright even amateur astronomers with good telescopes can see it if they look for it in the right part of the sky. If you somehow fell into a black hole, it might change your future and erase your past. Well, at least theoretically. Let's start with the real world we live in. Here on planet Earth, your past can definitely define your future. But imagine you're not on Earth, but somewhere out there in the endless universe, and you stumble upon a certain type of black hole. The one that a UC Berkeley mathematician found. Not to mix it with a regular black hole, let's call this type, what about a benign black hole, huh? So here's why you need a specific black hole. Thing is, you're highly unlikely to stay alive in a regular black hole. But according to some calculations made by a postdoctoral fellow, Hints, from UC Berkeley, this specific type of black holes we agree to call benign ones might expand at an accelerating rate. This is what makes it possible to survive the transition from our deterministic world to a black hole, which is not deterministic. Let's imagine you survived that passage, and now you're moving towards the center of a benign black hole. It's impossible to picture what's inside, and if you, as a traveler, could actually get into a black hole, you'd never be able to communicate to the outer world what interesting things are hidden in it. But it's not what interests us for now. We need to know how to get rid of the past. Hints, the mathematician you already know, studies non-rotating black holes that have an electric charge. The most important thing about them is that besides the event horizon, they also have the Cauchy horizon. And here's the point. The Cauchy horizon is the place where so-called determinism simply breaks down. This may sound too scientific, but let me explain it to you. The Cauchy horizon is the place where your past doesn't determine your future any longer. So, here's a mathematically proven and apparently working method of how to get rid of your past. All you need to do is get into space, find a specific black hole, make it to the center, and get to the Cauchy horizon. However, if it sounds too complicated, you can simply try not to make mistakes here on Earth. Yeah, ideas like your past gets cancelled, you have an infinite amount of options of how your future will evolve, and all that jazz sounds as unrealistic as they are appealing. Like, imagine no one knows you failed to get into college and get a degree, but from now on, you have every opportunity to do whatever you want. But only theoretically. In reality, once you get into the black hole, not that specific one we've already talked about, you're most likely to disappear once and for all. But hey, don't be sad. I'm only talking about your current physical form. It's a bit deeper than it might seem. Thing is, there's a curious principle of quantum mechanics that can be explained in a simple way. For starters, imagine that you're not a human being, but just information. You have your experience, your background, and your thoughts. All of these are the information you are. Now, let's make it even simpler. Imagine a USB drive or a book. Both of these things contain information. If you smash a USB drive that contains music and movies, it won't exist anymore in its physical form, but the information it had will never stop existing. Same with the book. If you burn it, the information it has doesn't get burned. It continues to exist, but in another form. So, this fun theory claims that even though someone passes the horizon of events, which is a point of no return before you get spaghettified, they don't stop existing. In simple words, these universe travelers still exist, but in the form of information. Now let's go back to the black holes. According to Stephen Hawking, black holes emit radiation. Radiation makes them shrink, and with time, I mean much time, a black hole can shrink so much that it eventually disappears. So what happens to the astronaut who got entangled in a black hole if it disappears? Nope, they won't be ejected from the black hole in the way they used to exist. However, they will still be ejected from there, but in the form of Hawking radiation. But it's just a theory. Right, you remember that no one knows exactly what happens in the black hole? Another theory says that what happens in the black hole doesn't really stay in the black hole. Sounds like a good alternative to Las Vegas if all the flights for the weekends have been booked. Some scientists believe that a black hole might have a portal where you can turn back time. According to this theory, there's a white hole at the end of a black hole. If you get there, you can undo things. Like, you broke your mom's favorite vase? Hop into the white hole and it'll be as good as new there. You cooked a scramble and made a fresh orange juice, but somehow lost your appetite. It's not a problem if you cook it inside a white hole. Voila! The eggs are unbroken. The oranges are uncut and juicy again. No more food waste. Alright, turning back time sounds really cool, so I guess we might actually need a black hole to help us out. If a black hole was made in a, let's say, lab, it could devour things until it grew big enough to consume the entire planet. First, it would munch on the Large Hadron Collider, which might possibly create something similar to a black hole here on Earth. Next, Geneva, where the Large Hadron Collider is located. Then the whole country of Switzerland, then Europe. At that point, it wouldn't be long before the Earth was gone too. Luckily, if a black hole did appear, it would be so small that it wouldn't be able to do anything. Black holes actually produce a lot of energy and release it, often as heat, like a furnace. That means they will fade away when they run out of fuel. Even if a stable microscopic black hole was created, it would grow so slowly that nothing would happen. Assuming that it survived long enough to absorb the tiny particles around it, a black hole of this size would take super long to get even a pound of weight. I won't be around then. But a black hole on Earth could be a great thing. Even a relatively small one may emit enough energy to completely power humanity. We're talking a lot about food, huh? Let's not forget about spaghettification. The concept is quite simple, by the way. It's all about gravity. Imagine you're playing with chewing gum. With your force, you can easily stretch it so instead of a regular piece, you can get a long and thin one. The same happens to you. Black hole force is enough to stretch you as if you were a piece of chewing gum. Gravity holds you tight on one side, which makes you stretch. You may wonder, how come you don't get spaghettified on Earth if there's gravity too? Easy peasy. It's just too weak to do that with you. If you asked a butterfly to stretch the gum, would it be able to do that? Not likely. Their tiny limbs are just too weak. Same here. The Earth is just too weak compared to a black hole. So, if you were wondering whether you'll ever reach 6'6", it may never happen on Earth. But once you're in a black hole, you can go far beyond those mere 6'6 inches. Your best height moment won't last long though. If you stretch the chewing gum at one moment, it will simply tear apart. The same will happen to you because of spaghettification.
If the multiverse theory is correct, ours is not the only one out there. Which is as interesting as it is scary, right? Now, not every scientist is on board with this mind-bending concept. And let's be honest, the idea of actually making contact with these parallel universes sounds about as probable as winning the lottery while riding a unicycle. But hold on tight, because this strange concept isn't just limited to the realms of fiction anymore. Believe it or not, a bunch of scientific theories actually support the existence of parallel universes. And let me tell you, it's a topic that stirs up quite the debate in scientific groups. Now picture this. The universe we live in is mind-numbingly vast. We're talking billions, some say even trillions of galaxies swirling around, each packed with an almost uncountable number of stars. Some brainiacs studying the universe's shape suggest that its diameter could span a staggering 7 billion light-years. Others even argue that it might be infinite. Could there be more out there than meets the eye? Well, real scientific theories are exploring the possibility of universes existing alongside, beyond, or even mirroring our own. These intriguing concepts of multiverses and parallel worlds often intertwine with other, more familiar scientific ideas like the Big Bang, string theory, and quantum mechanics. In order for us to figure out what's out there, we have to rely on the information we're a bit more confident in, right? Let's rewind the cosmic clock about 13.7 billion years ago. Everything we're able to see today was squished into a minuscule singularity. Then, if the Big Bang theory is to be trusted, it all went boom. The universe inflated with a speed faster than that of light everywhere, within less than a second. The way the universe went pop has led some clever researchers to ponder the existence of more than one universe. They question whether that sudden growth ended everywhere at the same time. While the expansion ceased for everything we're able to see from Earth 13.8 billion years ago, cosmic inflation might still be ongoing in some other mysterious corners. Some theoretical physicists say that as inflation ends in one place, a new balloon universe forms. But here's the catch: you can't just hop from one bubble to another like intergalactic tourists. These bubble universes are expanding indefinitely, and their edges are zooming away from us faster than light can travel. And here's where things get even more confusing. Let's say we somehow manage to reach the edge of our local balloon and encounter the next universe. Well, those same theoretical physicists mention that the neighboring universe could be a whole different ballgame. It might have completely different laws of physics, making it a bizarre place for us. Following the same idea, some say that in this vast multiverse of bubble universes, there might be other life forms just like us. The problem is, we're getting farther away from them with each passing moment, and our paths will never cross. Other super smart researchers out there are trying to connect parallel universes with quantum mechanics. Now, quantum mechanics is basically the fancy math behind teeny tiny particles. According to it, these particles can exist in multiple states all at once. They call it a wave function that holds all the crazy options. But here's the catch. When we observe these particles, we only see one outcome. It's like the universe keeps playing hide and seek with us. Now, there's this theory called the many worlds theory that says whenever we observe one outcome, another universe pops up where a different outcome becomes real. It's like our universe acts as a giant tree, constantly branching into countless versions of itself. These alternate universes can't mingle, though, so you wouldn't even know if there are a bunch of other yous living slightly or totally different lives. This many worlds theory is pretty bold and a bit hard to prove or disprove. And that's not great for science because scientists love to test and experiment with their ideas. But if there's infinite space out there, why wouldn't there be infinite universes too? Try to imagine the universe as this giant cosmic playground. Some specialists believe that if it's indeed never-ending, then there's only a limited number of ways that its building blocks can arrange themselves. Eventually, they have to repeat certain patterns. If this is true, then it may be possible that somewhere out there might be another version of you living the exact same life, even down to what you had for brunch yesterday. Did we ever have any proof of these supposed parallel universes? Well, some say we did. Have you heard the tale of the mysterious man from Taured? It's the story of a man that ended up at a Japanese airport saying he was from a totally unknown country called Taured. Now, some folks think it's proof of time travel, while others believe it's evidence he came from a different universe altogether. As much as you'd like to believe the story to be factual, the tricky part is this Taured place. There's a reason you haven't heard of it. There's no Taured to be found, whether in the present day or back in the 1950s when this supposed incident happened. After the airport incident, the man just vanished into thin air a day after arriving in Japan. Poof, gone forever. Let's rewind to that fateful day in July 1954 when the man from Taured supposedly landed in Tokyo. Descriptions paint him as a bearded, French-speaking man. Nothing too outlandish so far, right? Depending on who's telling the story, things start to diverge a bit. In one version, when the man hands over his passport to get stamped, the Japanese officer's eyes bulge out. While the passport looked legit, the country listed as Taured isn't recognized by anyone, including the officer and other officials. Naturally, they take our Taured visitor away for a little Q&A session. In another version, the man straight up tells the officer he's from Taured and shows him the passport when he doesn't buy it. Our man from Taured then started trying to convince the officers that his homeland is the real deal. According to him, Taured sat snugly between France and Spain and would have been around for about 1,000 years. To prove his point, he even points to the area on a map that matches the Principality of Andorra. Obviously, things took a mysterious turn. The officers decided to hold the man in custody, suspecting he might be up to no good. They put him up in a nearby hotel for the night, but not without stationing 2 people outside his room to keep an eye on things. Can you guess what happens next? Drumroll, please. When the officers showed up the next morning, ready to continue their investigation, the man had vanished without a trace. No sign of escape, and to make matters even more puzzling, all his personal documents have magically vanished too. What if the man from Taured was a time traveler or an intergalactic adventurer? Some have even delved into the realms of science fiction to explain this bizarre event, and you won't believe the number of people on the internet who've latched onto it as evidence for alternate realities. One of the weirdest ideas suggests that the man accidentally stumbled into a parallel dimension and ended up at the Japanese airport. In that parallel universe, there's an Earth just like ours, but instead of Andorra, they call it Taured over there. Another idea floating around was that the man was a time traveler from the future. Sorry to break it to you, but the most reasonable explanation for the whole story of the man from Taured is that someone's imagination went wild. Since there are many versions of the same story, it's probable people just kept adding outrageous details to the case, to make it more sensational. The whole story simply snowballed into an urban legend, and there's little to no reason to believe we've once seen a time traveler or intergalactic hitchhiker right here on Earth.
Brace yourself. You're about to hear one of the most unusual sounds ever. It's come from space, and it's the sound of 2 black holes colliding. But first things first. Our ears are designed in a special way, which helps us translate sound waves. But these sound waves become mute once the medium they're traveling through comes to an end. It happens when, for example, the atmosphere of Earth gives way to the vastness and emptiness of the cosmos. At the same time, there are some sound waves that can move even through a vacuum. And we can translate these vacuum-friendly waves into sounds our human ears can hear. That's kind of like radio transmissions work. Over the past few decades, people have sent quite many satellites to the far reaches of the solar system and even beyond. These spacecraft are equipped with sensors designed to hear such things as radio and plasma waves flowing freely through interplanetary space. These instruments are crucial for research and communication reasons. An additional bonus is that now we can finally hear different kinds of space waves as audible sounds. The results are often ear-splitting sounds, and sometimes audios are downright scary. Usually, when two black holes collide, they don't produce a sound. And still, thanks to modern technologies, we can now listen to this terrifying cosmic event. Do you hear it? This chirping sound is the sound that two black holes produced while slamming into each other around 1 billion light years away from our planet. Interestingly, the tone of the sound rises when the holes spiral closer to each other and stops abruptly when they eventually merge. Now, do you hear that long, low buildup? It means that the merger is quite slow, more sedate, and the black holes taking part in this event are relatively lightweight. A more abrupt chirp is a sign of a fast merger, where the black holes are rather large. For example, the pair that produced this sound combined and created one black hole more than 80 times the mass of the Sun. Since each of these black holes weighed as much as several stars, they were hefty enough to produce waves while passing through space. I mean gravitational waves. They are undulations in the fabric of space-time, fanning outward at the speed of light. You can probably compare them to the ripples that appear on the surface of a pond after you throw a rock in the water. Naturally, the sound of black holes colliding isn't the only unusual noise recorded by our equipment. NASA's Juno probe passes by Jupiter every few weeks at a speed of up to 130 miles per hour and plows through all kinds of invisible fields in the process. And one of the most powerful signals it has recorded is Jupiter's bow shock. That's the point where the planet's magnetic field pushes against the incoming wind of solar particles. The sound produced during this standoff sounds similar to a sonic boom. Or this sound. It was produced by the Stardust space probe when it was passing through the dust left by Comet Tempel 1. In the process, debris hit the body of the spacecraft. It sounded as if some creature was rapping at the window or hurrying across a hard floor. Let's have a look at NASA's nuclear-powered Cassini spaceship. It spent 13 years exploring gas giant Saturn and its numerous potentially habitable moons. This mysterious and a bit spooky sound is actually radio waves emitted by the massive planet. Such waves are caused by a phenomenon which is similar to the one producing auroras on Earth. Speaking of our own planet, it's surrounded by plasma. It consists of hot, ionized particles generated by sunlight. They're constantly slamming into Earth's atmosphere. NASA's Polar mission, which was launched a few decades ago, managed to record this breath-like hiss. That's what plasma orbiting our planet sounds like. As for these weird sounds, NASA doesn't say which space probe recorded them, but they're coming from Jupiter's largest moon, Ganymede. It could have been the Galileo spacecraft, which orbited the system for around 8 years. But it probably doesn't matter so much. Just listen to this creepy noise that sounds like screams trying to break through from some hidden place.
Black holes are the universe's most enigmatic entities. Their voracious nature lets them devour anything close enough, growing in size with each feast. But what's the range of their sizes? Dive in with me. To give birth to a black hole, you need immense gravitational collapse. Typically, this collapse results from massive stars exhausting their life. Imagine condensing the sun to a mere 1.8-mile diameter, or compressing Earth to pea size. What results? An incredibly dense object with immense gravitational pull, a black hole. While we commonly think of colossal black holes, tiny ones might exist. Known theoretically as primordial black holes, they could be minuscule, down to atomic dimensions. These ancient entities might predate even atoms, originating just post the Big Bang. Back then, with the universe in a tumultuous state, even a slightly denser particle might have become a black hole. These atom-sized black holes might weigh as much as mountains, while those weighing like Earth might only be coin-sized. Though fascinating, their lifespan would be brief due to extreme temperatures making them evaporate swiftly. Our universe houses the known category, stellar black holes. Their mass is often multiple times that of the Sun. For context, the Sun's weight is a mind-boggling number with 30 zeros. The smallest recognized black hole is 2, 4 times the Sun's weight. It drifts through space, hunting for cosmic prey. Gaia BH1 is our nearest neighbor, with 10 times the Sun's mass. At a staggering distance, M33X7, some 3 million light-years away, currently consumes a blue giant far bigger than the Sun. Transitioning to larger ones, we find intermediate mass black holes. They achieve their size by either consuming numerous stars or frequently merging with other black holes. A prominent example weighed 142 solar masses, overshadowing some earthly regions. A pair was recently spotted in a galaxy 17 billion light-years away. Though they'll eventually merge, their current interaction unleashes enormous energy. But the true behemoths in this category are the supermassive black holes. These cosmic giants have masses millions or even billions of times greater than the Sun. The colossal nature of supermassive black holes is baffling. How did they grow so immense in a universe that's only 14 billion years old? Enter quasi-stars, hypothetical stellar titans that dwarf even the largest known stars, like Stephenson 2.18. These could have birthed from the universe's early days, with cores collapsing into black holes even before fully forming. Inside a quasi-star, its newborn black hole would feed on the star's matter, growing larger while maintaining the star's equilibrium. Over millions of years, the black hole would swell, resulting in the supermassive black holes often found at galaxy centers. Contrary to belief, galaxies don't orbit these giants. For instance, our Milky Way's heart houses Sagittarius A, a 4 million solar mass black hole, just 17 times the Sun's size. However, not all black holes are dormant. The one in BL Lacertae gobbles up vast quantities of gas and dust. Then there's the black hole in Messier 87, captured in humanity's first black hole image, capable of swallowing our solar system up to the Orion Belt. But the universe harbors even grander entities, ultramassive black holes. These monsters outshine thousands of galaxies, drawing in everything in their vicinity. OJ 287 Center features one weighing 18 billion solar masses, so vast another black hole orbits it. Lastly, meet TON 618, the universe's largest known object, with a mass surpassing 66 billion suns. Its brightness exceeds 100 trillion stars, illuminating even from 18 billion light-years away. The enigma? We're observing TON 618 from 10 billion years ago. Its current size remains an awe-inspiring mystery, likely magnitudes larger than our last glimpse. Black holes are ruthless. They can swallow asteroids, comets, planets, and even stars. But can a black hole consume the entire universe? Almost any black hole was once a massive star that collapsed in on itself and became incredibly dense. Black holes have immense gravitational pull. Even light can't escape their clutches. The idea that a black hole can swallow the universe is based on a common misconception. People often think that black holes work like vacuums, pulling space inside. But that's not the case. Black holes can only swallow stuff that is extremely close, usually space objects venturing into their event horizon. That's a black hole's point of no return. Once you cross this border, there's no escape. The event horizon for a black hole with the mass of our sun could extend a mere 2 miles. If a tiny black hole had a mass of our planet, its event horizon wouldn't stretch for more than a couple of inches. It would be the size of your thumb, no more. But a black hole's gravity still affects the stars and planets surrounding it. It might make them orbit, just like the black hole at the center of the Milky Way galaxy does. But the hole doesn't swallow them. If our sun somehow transformed into a black hole with the same mass, which is highly unlikely, Earth wouldn't feel any difference in the gravitational force influencing it. Our planet wouldn't change its orbit or hurtle toward the newly born black hole. Of course, it would get very dark and freezing cold, but being pulled inside a black hole wouldn't be a concern. Plus, most black holes are quite small. A black hole can only swallow a star if the said star is aimed almost directly at the black hole. Theoretically, it might happen. But according to space experts, for the sun to get swallowed up by a black hole at the center of our home Milky Way galaxy, a truly enormous amount of time would be needed. After all, the star's orbit would need to line up with the black hole in a very precise way. Even the largest black hole in the universe that we know about, a space titan called Ton 618, seems to be near the theoretical limit of how large black holes can grow. This limit is determined by the fact that black holes release tons of radiation while developing. This radiation heats up and ionizes the matter surrounding the black hole, which makes it more difficult for the dust and gas to cool down and fall into the black hole. As a result, it slows down the rate at which the black hole can feed. We can probably say that this self-regulation stops black holes from gobbling down entire galaxies, let alone the whole universe. And we shouldn't forget about the expansion of the universe either. Objects in space move farther apart, which makes it less likely for them to collide or get captured by a black hole. If a black hole were to consume the entire universe, it would require a tremendous shift in the direction in which space seems to be moving. So, you don't need to worry that one day, our whole world will disappear inside a huge, universe-swallowing black hole. Unless, of course, the universe is already inside a black hole. I'm not kidding. There's a theory that we might be living in a black hole. Think about this. What if a black hole already engulfed us long ago? Surprisingly, some physicists deem this theory pretty plausible. For example, Dr. Nikodem Poplawski, a theoretical physicist from Indiana University, states that everything that a black hole swallows may turn into a new universe inside the hole or on the other side of it. So who knows? Perhaps our universe used to be quite a different place until it got pulled into a black hole.